Hello Physics 1 students and welcome to Lab 10. Today we're going to be talking about circular motion. And so as per the usual, I'm going to start off with a meme. So we've got Dwight here from the office. What goes around comes around. False. The only reason that something that goes around will come back around is if it is affected by centripetal force. So we're going to talk about what centripetal force is today. So centripetal, if we break down the word, centry is center and pedal is seeking. So it literally translates to a center seeking force. And with no centripetal force, an object would travel linearly, as we talked about with Newton's first law, right? An object in motion will stay in motion at a constant velocity until acted upon by another force. So you can see right here, I've illustrated a really simple centripetal motion, right? So this object, this mass is traveling in a circle, and you can see that our centripetal force is directed inward, right? Maybe it's tension in a string, or as you're going to see in this video, maybe it's somebody's arms holding onto a merry-go-round. However, as this mass is moving around in a circle, the linear velocity or the linear speed is going to be tangent to the circle. So as this mass moves, the tangent line is going to adjust, right, to be tangent to the circle at all times. And so essentially what this linear velocity is illustrating, what this vector is illustrating, is what the mass would be doing if this centripetal force were not here. So if there were no tension in the string, if this person were not holding onto the merry-go-round to keep holding themselves in this circular path, they would move out tangent to the circle. So I thought a really good example to show this is actually a fail video on a merry-go-round. So without further ado, let's watch and observe the centripetal force. So here you can see these guys are moving right in a circle, and their arms are actually going to be providing the centripetal force here. Okay. Now when their arms are no longer strong enough to hold them in a circular motion, you can see he flew out linearly, right, tangent to the circle. All right, let's watch that one more time. So what we're looking for here is we're going to see that once there is no centripetal force, once this guy's arms fail him, and he is no longer able to hold himself in this circular motion, he is going to fly out tangent to the circle, which is what his linear velocity is. Okay, so let's watch that one more time. So here he's still able to hold himself in the circle, right? But now as they go faster, it requires a greater force, and you can see a perfect illustration how he flies out perfectly tangent to the circle. All right, so let's get back to the slides here. So an overview, centripetal force, that is the net force on an object traveling in a circular path. Without the centripetal force, the object will not travel in a circular path. So if you think about like a mass on a string, so you could think about, this circle that's being illustrated here, maybe this mass is being swung around on a string. So it would actually be the tension in the string that's holding this mass in a circular pattern. If you were to release the string, just like the guy in the merry-go-round, you would fly out, the mass would fly out tangent to the circle, right, at v linear. So that's what the velocity is. So obviously as it moves around the circle, the velocity is going to change at each instant, right, because it's always going to be tangent to the circle. On the other hand, the acceleration, so the centripetal acceleration, that's going to be radial and directed inwards towards the center of the circle. A couple other terms that are pretty relevant to centripetal force is the radius. So the radius of your circle for your circular motion, right? And I'm going to highly encourage that when you're given a radius that's not in meters, you convert it to meters before you draw your picture, because of course we're going to be working with forces, right? And newtons are kilogram meters per second squared. So I have a similar caution for you with mass. If they give you the mass in grams, go ahead and convert that right to kilograms. And then the period will typically be given to you in seconds. But if it weren't, you would want to make sure that it's in seconds. And the period, of course, is the time that it takes the mass to travel around the circle once. So the amount of time it takes for it to get from this point all the way around back to this point again. All right, so now I want to draw your attention to equations. So here are our most important equations. There are 4 of them for centripetal force. And the way that you're going to calculate centripetal acceleration, you can see that it's mentioned here a couple of times, right? The way that you're going to end up calculating centripetal acceleration will depend upon the information you're given, right? So if you're given the centripetal force and the mass, you're probably going to calculate it using this formula. If you're given the mass and the radius and the period, then you're probably going to calculate it this way, okay? All right, so without further ado, centripetal force, just like we know from Newton's second law, that is equal to our mass times our acceleration, specifically the centripetal acceleration this time. And remember that centripetal force is the net force on an object traveling in a circular path, right? So this is the force that is making sure that this object keeps traveling in a circular path. Without it, it would not travel in a circle. It would travel in a straight line. Okay, number 2, angular speed. So this can also be represented by omega, which looks like a little W here. So if you see omega, that's angular speed. And this is equal to 2 pi over the period, and the units are radians per second. Linear speed, this is typically depicted as a lowercase v, okay? And this is either omega times r, so your angular speed times the radius, or if you want to expand it, then it would be 2 pi r over the period, right? And these units would be meters per second, just as we're typically accustomed to seeing for speed. So if you're asked on one of the quiz questions and they want to know what is the speed and they don't ask you linear or angular, look at the units for the answers. If the units are in meters per second, you're looking for linear speed. If the units are in radians per second, you're looking for angular speed. All right, and then last but not least, the other way of calculating centripetal acceleration, that's going to be your linear speed squared divided by your radius. And then just a little side note, I'm sure you noticed the asterisks over here, that speed, we're saying speed because the displacement is technically 0 for each revolution, right? So just keep that in mind. That's why we're saying speed, not velocity. All right, so just a little bit of theory here. So where does centripetal acceleration come from? So we know from lab number 2, right, where we talked about what velocity is and what acceleration is. We know that acceleration is our change in velocity over a given time, right? So what I've done here is I've taken this vector, this blue vector, this arrow here, and I've copied it and I've pasted it over here. So this, I'm going to call this guy V1, all right? Now, as we move on, so we travel around the circle, some time has elapsed, we have V2, right? So this vector, once again, is copied and pasted here. Now, the change, so right between these two vectors, the change in the velocity over that time, delta V1, that would technically be acceleration, right? Because the definition of acceleration is our change in velocity over a given time, right? So you can start to see the pattern emerge, right? How you get centripetal acceleration is this radial inward vector, right? We can keep doing this multiple times, V2, V3, this is the change vector here, this is it copied and pasted over here. And you can go all the way around the circle and you see this is where that centripetal acceleration is coming from, right? It's just the change in velocity over the change in time, okay? So there you have it, changed it from delta V to a subscript c, right? Because that's what it is. Centripetal acceleration is technically our change in velocity over our change in time. And this is just a recap of everything that we talked about before. So this is all of our equations, so that they're just fresh in your mind. And without further ado, let's start Prelab 10. Okay, so there are 6 problems in Prelab 10. Let's do problem number 1. So problem number 1 says, what is the angular speed of this mass? And the prompt here is there is a 350-gram mass tied to a string and spun in a horizontal circle with a radius of 11 centimeters. The speed of the mass is held constant and the period of rotation is 0.65 seconds. So you can see I filled in our mass is 0.35 kilograms, right? 350 grams is 0.35 kilograms. The radius, they tell us, is 11 centimeters. I went ahead and converted it to meters, so the radius is equal to 0.11 meters. And then the period of rotation is equal to 0.65 seconds. So the first thing that we're looking for, pre-lab practice problem number 1, is the angular speed. So to review, right, angular speed, just grab this equation from here. So the angular speed, or omega, is equal to 2 pi over the period. So all we do is we take 2 pi, we divide it by the period that we were given, and we get that the angular speed is 9.67 radians per second. Number 2, what is the linear speed of this mass? So now we're looking at v linear here. This vector is what represents v linear, that's why it's highlighted. And the equation that we're going to use is omega times r, which we also know if we expand it is 2 pi r over the period. Well, since we already calculated omega, the easier way to calculate it is just to do omega times r. So that's just 9.67 radians per second times 0.11 meters, and you get 1.06 meters per second. That is our linear speed. Number 3, what is the spatial orientation of the linear velocity vector? So once again, it's highlighted because that's the one that we're talking about here. So the linear velocity vector, we can see that it's tangent to the circle, right? And if we look at the prompt, we can see that it's spun in a horizontal circle. So we also know another thing about our spatial orientation. It's a horizontal circle, and it's also tangential, so that makes the linear velocity vector horizontal and tangential to the circle. Number 4, what is the magnitude of the acceleration of this mass? So the formula for centripetal acceleration is our linear speed squared divided by our radius. And so we know our linear speed is 1.06 meters per second. We're going to square that, and then we're going to divide it by our radius, which we know is 0.11 meters. And so we get an acceleration of 10.3 meters per second squared. All right, number 5, what is the spatial orientation of the acceleration vector? So you can see it's highlighted right here. This is our acceleration vector right here, and it is radial, right, as we talked about. It is radial to the circle. It lies along a radius, and still same circle, horizontal. So that makes the spatial orientation of the acceleration vector both horizontal and radial to the circle. All right, and last but not least, problem number 6. What is the magnitude of the centripetal force on this mass? So now we're going to calculate centripetal force, right, which we know is mass times centripetal acceleration. So we know the mass is 0.35 kilograms. We calculated the acceleration, the centripetal acceleration, which is 10.3 meters per second squared. And so we get that the centripetal force on this mass is 3.61 newtons, or essentially the tension in the string is 3.61 newtons, and that's what's keeping it traveling in this circular path. All right, so that's it on the pre-lab practice problems. So now I'm just going to review some kinematics, because as you know, the quiz will have 5 questions from circular motion, but there will also be questions from previous topics, which this week, spoiler alert, is going to be on kinematics. So some kinematic relationships. Hopefully you haven't forgotten these from lab 2, but if we have a constant acceleration, our position versus time graph is going to be parabolic and look something like this, most likely, right? So we have an upside down parabola. So typically when you're taking your slope of your position versus time graph, you're going to be getting velocity, right? So either you're taking the slope of the tangent line and you're getting your instantaneous velocity, right? Or you're taking the slope over a broader period from t initial to t final, and you're getting your average velocity, right? Now, if we come over and we look at our velocity versus time graph, if we take the slope of that graph, well, it's going to be the same everywhere, right? Because it's a line, so the slope of the line does not change. But in this case, the slope of the line is going to be our acceleration, right? So you can see right here, slope is equal to g, right? Because constant acceleration, this is on Earth. I'm saying that our acceleration is gravity, right? So that means that the slope of this graph is gravity because that's the acceleration. Then if we come over here to our acceleration versus time graph, of course, we know it's a constant acceleration, so no surprises here that we have a flat line right at our acceleration, which is gravity. Now, something that you'll probably see a little less commonly is when you have a linear position graph. So basically this means that you have a constant velocity. So this one, you had a constant acceleration. This one, you have a constant velocity. Okay? So if you have a constant velocity, you have a linear position versus time graph. But just like we had before, if we're taking the slope of our position versus time graph, we're going to be getting the velocity, right? Remember over here, we were getting the velocity when we took the slope, either way. Well, same thing here. The only thing is now this is a line, right? So that means our slope isn't changing, which makes sense, right? Because it's constant velocity. So we shouldn't have our velocity be changing if it's constant, right? That if we come and we look at our velocity versus time graph, should come as no surprise that it's going to be a flat line, right? It's going to be the same velocity no matter when you are, because we have a constant velocity. Then if we look at our acceleration versus time, it should also come as no surprise that our acceleration is 0 meters per second squared, because acceleration is the change in velocity over the change in time. If the velocity is not changing, then there can't possibly be an acceleration. So just keep those concepts in the back of your mind as you're taking the quiz. They will probably come in handy. All right, so Newton's second law. So if we have some mass and it's being pulled by F pull, that's our net force, and possibly being opposed by friction, right? Because you can see we drew friction in here. It's on a horizontal surface, and so we have our normal force, which is being equally and oppositely opposed by the weight force. And then our direction of motion is in this direction, right? So in the direction of our net force. So if we want to sum up our forces in the x direction in order to calculate our acceleration, it's going to be F pull minus our friction force is equal to whatever this mass is times the acceleration, right? So that would be what we would be solving for. If we were trying to find the normal force, it's a horizontal surface, so pretty straightforward. This is just a horizontal force, right? So there's no vertical component. So all we have in the y direction is normal force minus the weight force. So we know that our normal force is going to be equal to our weight force in this case. All right, and then this is review from last week. So if we have motion on an incline, and this is the scenario with no friction, so here's our mass, right? It's sliding downhill. This is the direction of our acceleration. What's making this move, what's driving this mass downhill is mg sine of theta. That's the external force driving the system. Then for the normal force, it's a little bit different when we're on a slope, right? The normal force is equal to mg cosine of theta, right? Because we talked about last week how this angle, theta, is the same between this perpendicular line with the surface and this weight line. So we have mg straight down here, and then this line that's perpendicular to the surface, that makes that same angle theta as the slope here, right? So we know this is our adjacent side, mg cosine of theta. This mass isn't bouncing all over the place, so we know that it's balanced by the normal force. So mg cosine theta in the positive direction opposed by mg cosine theta in the negative direction. Okay? Then in terms of things that you'd probably have to solve for, you'd probably have to solve for your acceleration, an experimental gravity value like you did in Lab 9, or what the angle of your slope is. So as I mentioned before, the force that's driving this motion is mg sine of theta, right? So when you're summing up your forces in the x direction, you have mg sine of theta is equal to m times a, right? So the m's cancel, so you're left with g sine of theta is equal to a, right? So if you're trying to find the acceleration, that's it. You've got it made in the shade. It's just g sine of theta. If you're trying to find the experimental value for gravity, right? Because you've recorded some accelerations, right? Well, then it's going to be a over sine of theta, right? Because all you're going to do here is you're going to divide a by sine of theta. We'll divide both sides by sine of theta, so you get g by itself, and you get that g is equal to a divided by sine of theta. Then last but not least, if you're trying to find the angle of your slope, you're going to use inverse sine of a over g, and that's because we know that sine of theta is equal to a over g, but since we're trying to find theta, we want to use inverse sine, so there you are. Inverse sine of a over g is equal to theta. So hopefully you found this helpful, and best of luck on quiz 10.